Okay, so we finished the basic part of the lecture. So I'm not going to save the slides there. Okay, and we are going to come back to this. Okay, yeah, so we will look at this in a minute. Y is y times theta x be the distance between the hyperplane and the point. Okay, so we try to cover that. Okay, so let's go back here. Let me try to pull up the slides. So in the support vector machine, basically we are looking at this part, all right? We want to be able to define the distance to the nearest points as a unit distance, okay? From here to here, right? So we just want to guarantee that all of the points will have satisfy these two inequalities, okay? That means that the theta values, which are our slope, right, are theta 1 and theta 0, okay, x, okay? These two values times our points, these are our points, right, our x's, okay, that they will have to have values that are above 0 or below 0, right? This is what it means to find a separating hyperplane, right? But we're going to make this even more restrictive, okay? We're going to say that it's not above or below 0, but above or below 1, okay? So this must be bigger than 1, and this must be smaller than -1, okay? Something like that, okay? And so that's why we are multiplying these two things together to get a distance between the hyperplane itself and its closest point, okay? We're measuring distance by a perpendicular distance from the hyperplane to the point, okay? When we make this convention, there's a set of math, which I can go over if you like, that help you convert this into a quadratic programming problem. But I think we don't need to cover that in too much detail. It's just that what we want to make sure is that we have all of the points, you know, all of the positive points over here have to have a distance from this hyperplane. Okay, so if we can think of it in 2D, this is the line, right? Okay, so our margin is basically this point over here, okay? That has to be larger than 1, okay? That's what we're going after, okay? And the same for this bottom point here, that it has to be smaller than 1, okay? So it has to be at least a distance, a gap of 1 away from here, okay? So hopefully that makes a bit more sense to you, okay? Actually, the interesting thing about support vector machines is it's really cool is that, you know, if you don't have a support vector, okay, if you're a point that's not a support vector, let's say, for example, the points over out here, like this one, and this one, right? These points don't matter at all, right? They don't matter at all because if they were there or if they were gone, the hyperplane wouldn't change, right? It would still be sitting where it is. And you can think about this in the perceptron case too, right? The perceptron case only looked at misclassified points, right? So as long as the point is correct, we don't care about it. We can't learn from correct values. We can only learn from incorrect values. Here, what we're saying is that all points that are not close to the hyperplane don't matter in the computation, okay? So the support vector machine is actually completely defined just by the support vectors, right? These guys over here, right? The ones that are sitting at the boundary, defining where it sits. They're called support vectors because they're like scaffolding, okay? They tell you exactly where that hyperplane is going to sit. It has to sit in the middle of these two boundaries, okay? So this is a really interesting thing because if you have a data set where there are very few support vectors, where it's very easy to locate the hyperplane, then the complexity of a support vector machine is very small, okay? When there are lots of irregularities in your space, even in your Z space, then it becomes very difficult to characterize. You might need a lot of support vectors, and then it's more complex, okay? So it again says that the quality of the support vector machine is based on the solution the solution quality is based on the complexity of your data set. Okay, so I think that is really cool because it's basically saying that not all the points matter, only the points that help to decide the hyperplane matters. Okay, so let's come back to another question that you guys asked about, which is about the Z-space. Okay, what exactly is the Z-space in SVM? It's the same as what we talked about earlier in nonlinear mappings, okay? So in the X space, we see points like this, okay? So there are red points and blue points, but when we map using a kernel function or equivalently a phi function, we get a space where the points are nicely separated, okay? And we can use a line to separate it, a straight line, right? A straight hyperplane, okay? So that's where we do the classification. We actually map using what we talked about earlier, a linear kernel or some type of kernel function of the points into a space that's on the other side in the Z space. And then we classify just the normal linear classification in this space over here, okay? So, you know, when we do support vectors, we have two ways of getting what we want, all right? We can do it, okay, both of these ways, okay? This part we are doing with this C, or the soft margin penalty, right? Soft penalty of errors, okay? And we can also do it this way, right? So we just talked about using our X to Z mapping, right? So we have a mapping function like that. You can do that by introducing a phi function, okay? This phi function or our kernel function can map things from one coordinate space to another. And even in this Z space, we can still use soft margin penalties, okay? So we can say, if I map this nonlinear space, this original space to this, to look like this, and I still have some things that are sitting on the wrong side, I can still use a soft margin SVM to cater for that. So it doesn't have to be exactly separable. It can be more or less separable with some tolerance for error, and I can still draw a nice straight line like the one that I'm showing you here that's going to classify the majority of the points with some amount of tolerance for error on both sides, okay? All right. Okay, let us go to the second part of the lecture because I think this is where people get really confused on bias and variance. Okay, and then we'll come back to some of the questions here. Okay, so I hope I've clarified why this is the case. Okay, the distance between the hyperplane and the point is just because we need to multiply them together to get the distance value between the hyperplane and individual points. Okay, so we've taken them off in two different parts. The coefficient b, we just separate because that's an intercept, but the direction of the plane is given by all of the x's, right? All the thetas here. So this is, the theta here is actually theta 1, right? Theta 1 through whatever theta we have otherwise, right? Where did my pencil go? I think. Okay, if I don't get to all of your questions or things like that because my computer keeps on dying, I apologize for that. Unfortunately, these things are not under control, my control, but under Windows control. So I will try to answer them on the forum. You know, I have the transcript of everything you guys typed, so I can do that later. Okay. So let me get your chat here. Okay. Yeah, I've used Linux a lot. You know, the problem with Linux is you have a lot of fumbling on other things. So yeah, well, I used to use Mac a lot and then I had problems with that. So I just had to find enough time to get things done. Sorry about that. But thanks for the suggestion. Let's see when I can open this up. Yeah. So we can have lots of debates about Macs, but I thought going back to Windows wasn't going to be that terrible. It turns out, unfortunately, I'm not very lucky. I'm using a new computer. It's a Surface Book, and it's still dying. It's only about a month old, and I have to go return it. Okay, enough ranting. Let's get back to bias and variance. So if you have more questions about SVMs, please let me know. I think SVMs are wonderful. If you know anything about the history of machine learning, is before people started getting so much data and finding ways to handle it, people were very concerned about the computability, you know, theory of computation. And in the 90s, 80s and 90s, a lot of the computational learning theory that looks at support vector machines and kernelization, all of that stuff, this great stuff in math came out then. So fortunately or not, I think it's really debatable. You know, things have gone the way of connectionists. So everything right now in the state of the art is deep learning. So we have no choice but to teach it because, again, this is something that I think a lot of employers expect you to know, some deep learning work. But as you will hear and complain about later on, for those of you who are more math inclined, deep learning does not have a very strong fundamental mathematical basis. It's sort of like very dissatisfying that it works very well. So a lot of people rant about that, and I completely understand that. Okay, but the crux of the thing is that now we have a lot of data, we need to fit it well, and this lecture on bias and variance comes even more important as a result of that. Okay. So I'm sorry if you get electrocuted with your MacBook. I've gotten, yeah, lots of electric shocks from the power cables on every laptop imaginable. But okay, let's not go there. I can waste a lot of time on that. Okay, so what we want to do is think about this trade-off. It's exactly what we are talking about between the difference between machine learning, which is about generalization, okay, and statistics, which is about approximation, okay? So that is what we're looking at, okay? What we want to do is ultimately, we don't care about our training loss, right? Who cares about training loss? Because that data is given to you. What we want to know is, will it work on unseen data coming from the same distribution? That is our test error, right? We want good approximation of the target function on unseen test data, but we don't have that much data to work with, right? So we have to make a choice, okay? We have many choices to make in machine learning, and although you can trust the computer for them for many things like AutoML, you should understand the basics, okay? So the first thing is when you take a look at, you know, which type of hypothesis class that you want to choose, right? So in this lecture, we have been talking about H2, H1, H10, etc., H50, okay? Meaning how many coefficients do you have to your function? Like H50 would have X50 all the way to X0, and we'd have coefficients for each one of them, right? So all the way from 50 to 0, so that means I have 51 coefficients in this case, right? So there's a lot of knobs to play with. So you can think about, like, say, a mixing board or something like that that you might see in a audio studio or production studio. That's what I mean, like having lots and lots of different things to control. Okay, when we have lots and lots of knobs, we have a much better chance of approximating the target function because, well, you know, if it's there, I will be able to find it because there's some setting of knobs that will allow me to produce the target function, right? But, you know, if I have different samples, okay, and let's say I get one sample here, one sample there, and each of these samples I can approximate F perfectly, but these different hypotheses that I come out with a more complex H are different, then okay, I'm screwed, right? I really want to make sure that no matter what type of sample I get, you know, regardless of what sample I get hypotheses that look more or less the same because actually they were generated from a single function. If every time I approximate F, it's wildly different, then you would say you're crazy. You know, you don't have a good handle on what it means to approximate F. Okay, so this is why we want to go for a smaller H. Okay, when we say again, when we say our conjunctive learner is only looking at conjunctions or of two different constraints on different drink values, that's what we're doing. Okay, and the best thing is, of course, that we have a hypothesis set that actually only has the target function, but we never get that, right? Okay, so what we want to do is figure out how to think about this test error, right? So if we have this test error, we want to know two parts, right? how well can it actually approximate the target function, and how well can I zoom in onto actually a good hypothesis that's going to reflect F, given that the size of H is a certain size, okay? So again, I told you earlier that in the 90s and 80s, there's a lot of work in SVMs that did a lot of interesting work to lead to this idea of shattering and VC theory. Again, we don't have time for that, but this entire idea also applies to normal types of classification boundaries. So here we're only looking at this case of linear regression. Okay. So when we start with the test error, basically we can say this. We saw earlier that when we think about test error, we have to think about the expected value of X, right? What's the expected points that we're going to get in to classify? Some points may be more common than others. So we are going to expect those points more. So our average X may not look at all of the funny outliers that are very strange, but concentrate on the middle set of data that we're likely to have, okay? So what we're going to say is that we're going to look at the hypothesis that this specific data set, our data set D, came up with, all right? And then subtract the actual value that I get, right? So the actual value of the function, this is the hypothesis that I come up with. I square the error, okay? And then after that, I'll get this estimate, okay? So what we're going to do is decompose this, right? So we're going to say, well, you know, this X, we have to think about this when we generalize over, okay? So yeah, how do we even know what the expected X is? Okay, so we don't know, right? We don't know. Sometimes we know because we have some sense of what types of data are going to happen. We can look at the training data or look at different samples of the training data and try to estimate what types of X that we'll get out. So this week, for example, when we get to validation, we'll have a better idea of how to calculate what is an expected X, okay? So that's a great question, okay? So yeah, we don't know what the real function is, but we have samples of the real function, possibly with noise, right? From getting a data set, okay? So we're gonna say, well, you know, we really want to know what's the expected data set like? Because we're not looking at a single data set, but we want to say, quantify over all possible data sets that we're going to get, what is the expected error, okay? Because we don't know which data set we're going to get, so we're going to go through the expectation over all of the data sets, okay? So we can write it out like that, okay? Because we can swap expectations, so we can reorder them whichever way we like, because the thing inside is not negative, then we can reorder this, okay? So now we have an expectation of X first, okay? And then for an expected data set, we have this part here, right? So what is the hypothesis for the data set look like minus the actual value? Square that, that's the error. We take that over all the expected data set and then over the expected X, okay? So we're gonna worry about this X term later. We'll just go ahead with the inside, okay? So what we're doing here is looking at what this quantity is. What does it mean for a hypothesis on a data set, okay? So what we're going to do is we're going to say, well, you know, I don't know what the actual data set that I'm going to draw is, okay? But, you know, maybe what I can define is an average hypothesis. Okay, an average hypothesis is sort of like what we were doing before when we had all those lines that we drew on the sine wave, right? We took samples of 2 points, we drew a hypothesis, we took another sample of 2 points, we drew a hypothesis, we took another sample of 2 points, we drew a hypothesis, and we're just going to average all of those hypotheses together, and we're going to call this H bar, okay? H bar of X, okay? And that is going to be basically what the hypothesis is for a particular data set, for example, a data set of 2 points drawn from the sine wave, okay, but over the expectation of all possible data sets, because all I have to do is say sample 2 points, sample 2 points, sample 2 points, sample 2 points. You can do this countless numbers of times, and then we're going to average all of their hypotheses together, okay? So that's what I'm doing. Imagine many, many, many data sets, of whatever size I want, okay? I draw k of them, so maybe k is some large number. Then I can say, well, my average hypothesis is going to be approximately something like this, right? I'm going to take all the hypotheses I got out, okay, all the slopes and intercepts, okay, they're all different lines. I'm going to just average them all out, okay, and that's going to be my hypothesis class, okay? So that is the idea behind the average hypothesis, okay? So once we have that, it's actually quite nifty, all right? So we're going to say using this idea of H bar, which is our average, let me get this off the screen, average hypothesis. Okay, which is, you know, doesn't care about the data set because now we've averaged it out over all data sets, right? Isn't that great? Then what we're going to end up with something like this, right? So we have the average of this, and we're just going to add this extra term here, okay? I'm adding unity, all right? I'm adding a plus H bar and a minus H bar into here. So that's this part here, okay? And I have this squared, right? This is the same as before. And then what I'm going to do is I'm going to span this out, okay? I'm going to span all of these cross terms out, and I'm going to associate them, okay? So let's see. When we do this, we end up with the cross terms over here, okay? And then we're going to end up with two terms sitting at the end. So basically, I'm saying this is term A, this is term B, and then I'm just writing out A squared, B squared, and then AB 2, right? So that's all I did. Okay, so I have two of these terms, one set from A, right? This is my A, this is my B, and I've got the 2 here. So this is just multiplying all the terms out, okay? No problem, great, so we do that, okay? And then what happens next, right? We can say these cross terms drop out, okay? Why did the cross terms part drop out? Because this thing is 0, okay? What's the difference here? Okay, what does this actually say? This says the hypothesis specific to a data set, right? And this is the average hypothesis, right? So why is this 0? Because over all of the different data sets that I have, this will be the same, right? This HD is over the expectation. So this and this are exactly the same thing, okay? So I can cancel this term out. So when I have a 0 here, this entire term goes away, all right? And I'm left with this, okay? Everyone follow that? This is probably one of the more complex parts of the proof. So I just want to make sure that you are all good with that. So if you're good, please put a yes for me. If you're not clear and you need to see this again, I will happily go over it with you again. The key part here is we're trying to get away from this notion of a dependency on a particular data set. We don't want to deal with particular data sets. We want to deal with the expectation of a data set, the average of a data set, okay? So when I do that and I can define this quantity of an average hypothesis, this average hypothesis and the difference between the average hypothesis and the particular term here is going to go away because these are going to average out, okay? Okay, I'm worried some of you are pretty confused, so we do need to make it clear that you guys are all good. So anyone confused, please let me know, unmute or chat or something to let me know that you need it explained again. Which squared term? So this one over here is not canceled out because this is for a particular data set, okay? It's only in this case here because we have this individual one is 0, but the squared is not 0. So this is, you know, some of these will be positive and some of these will be negative and these will cancel out, but their square doesn't cancel out, okay? So their square still remains a term that I have to think about, okay? Thanks for the question, Xueting. So I hope that answers that. Okay, so we'll go on. So actually it becomes really nice as an analysis, all right? We get two terms, right? One is saying the expectation of the data set, because the data set is still there, okay, as you can see from this last slide. This expectation is over the data set, but because this part, okay, cancels out, and this part has nothing to do with the data set, you don't see any dependencies on D here, we can drop the expectation, okay? So now I'm left with two terms, right? This says for an expected data set, okay, how much does the hypothesis of that particular data set differ from my average, okay? So if I can think about this case of the sine curve again, right? Let's say I get points here and here, and I get something like this, okay? My average hypothesis, if you remember, looked a little bit like this, okay? So I'm trying to determine what's the difference between this and square it, okay? So all of this error here is being squared, right? From my average, okay, which is in the red, to my specific hypothesis that's generated by my data set, okay? And then I have here, okay, this is the other part, right? Which is to say, when I have an average hypothesis, okay, again, let's take a look at this one here, and I have this average hypothesis, how good does my average hypothesis fit the actual function, okay? So I've got two terms here, bias and variance, right? So I want you to guess, okay? If you think the first term here is bias, then put a check, okay? And if you think the second term is bias, you put an X. Okay, so I'm going to clear the remarks, okay? Then please help participate. Which one is number one? Okay, I'll wait for a couple seconds here. Okay, you have to go back and think about this, okay? This is a key part of the lecture, so I want you guys to understand this, right? Okay, what we had was a sine curve or any other curve, okay? And we have a hypothesis, these are average hypotheses, right? And so what we're saying is, which one of these, this one part here is talking about the difference between a specific hypothesis, let's say we got this point and I regress this line, and I want to measure the error between this line to the average hypothesis. Which one is that due to? Is that due to bias or variance? Okay, so I think everyone now agrees that it's the variance case, right? Okay, so that's correct, right? So when we think about dependency on the data, this is always variance, right? We're saying when you sample data and you get different data samples, you get different hypotheses, right? So some of those hypotheses will be really close to the right one, and this term will be low, right? Because the actual hypothesis minus the average hypothesis will be low, okay? So that's good. But there will be cases in the case where we drew the sine wave and we sampled, let's say, these 2 points and we got something like this instead of something like that, where they'll be completely off, okay? And that is when the variance really is bad, right? The sample that you drew, this D, led you to this hypothesis over here, which is perfectly fine for the data that it got. It perfectly fit, right? Nothing wrong with that. But it just is a particularity of the sample, okay? And so we're not going to come anywhere close to this, all right? Now, the second part that we talked about is this bias, right? Bias is then saying, okay, how well can I fit? Is it better to use this function or this function to fit, right? Or H0, okay, best hypothesis under H0 or best hypothesis under H1. Of course, when we have a more powerful model to fit a more powerful target function, it will probably work better. We have more degrees of freedom here. At least we have slope in H1. We can fit the sine function better with H1, okay? So our bias error is lower because we have a more powerful model that can fit a more powerful function, okay? Are we clear about that? You need a function that is at least expressive enough to capture most of what is happening in the target function, okay? If you don't have that, then you have underfitting. You have a lot of error due to bias, okay? So that is where this comes in. Now, of course, that doesn't always mean, as we saw in the pre-part of the lecture, that we should use a powerful model, okay? Because a powerful model will fit everything in the data, including noise, including the particularities of our sample, even when the sample has no noise, right? Because if I sample points on this and I sample them exactly, let's say this point here, and this point here, and this point here, and I use, let's say, third order polynomial, let's say, let me add a couple more points, okay? A fifth order polynomial to fit these instead of a second order polynomial will get very large waves like you saw in the pre-part of the lecture, right? So we don't want that because then the variance will come out, okay? Even though we have high bias error, we would accept bias error over variance error because the variability in the hypothesis is going to come out really badly when we go this direction, okay? So that is the bias variance trade-off in a nutshell. Okay, what we want to do here is before we think about better ways to control this is to make sure we choose the right H. Okay, so we have a hypothesis class. We can choose either H1, H2, H10, H20. Okay, and we want to choose in such a way that we minimize the two sources of noise, either bias or variance. Okay. So when we came back to this idea of learning, right, we saw that when we have two learners, right, we said the overfitting model chooses exactly the same as the 10th order polynomial because this is a 10th order polynomial, okay, and it gets a 10th order polynomial in, but because the data is slightly inaccurate, okay, and you get some samples, all right, that are not actually on the line, we can't fit it directly, okay. So we fit a 10th order polynomial to it, but we get high variance, okay? So we need to think about when H2 and H10 are better than each other, okay? So we can think about it like this, all right? So here's our expected costs, our J train, okay? Or J test, okay? So if we put both of these on the same axis, then as you can see here, as we increase the number of points, okay, we are going to get better and better fit, okay, to our actual cost, okay. So why is that? Because our training error will go up. Why? Because our error, given the points that we have, will start to get so much that we cannot fit them exactly, okay. So imagine if you have only 3 points, okay, and you get a 10th order polynomial, you don't have any problem fitting all of those points, right? So at the beginning, your J train will be close to 0 if you have a powerful model. And as you introduce more and more points, the model can no longer fit all of the points, then our training error will go up. It will tail off, okay? It will tail off to some point over here, okay? And the same for our test case, right? Our test case, we're going to get larger error at the beginning, but as we get more data points, our training and testing distribution will start to converge, okay? And then we'll get something that approximates the training error. So this is the error in the limits, okay? So this is in the case of something like H2. So when we have something like H10, okay? H10 is a much more powerful model, so we can expect to fit the data better. That's why in the limit, the expected cost, okay? These two graphs are comparable, okay? The expected cost for our H2 in the limit and our H10 will be higher, right? So our H10 will work better once we have enough data points, okay? And the thickness of this gray area is basically that place, right? When we have M larger than this, okay, then it's better to use an H10 classifier, okay? So again, this is iterating this idea of why it's important to have a good idea of the data scale, right? When we have enough data, then the more powerful models can actually provide enough information to lower the test cost, right? Because we have a better model fit, okay? So we can do this by thinking about several different things. We can say when we compare our polynomials, let's say a second order polynomial and a 10th order polynomial, we compare their out of sample errors on these two classes, okay? We can calculate how much worse was it to use H10 over H2, okay? So we can graph that to come up with what we can call an overfit measure, okay? This is in the case where we're just simulating, okay, where we have the actual target function. So this is sort of like a thought experiment, all right? So we have a target function, we created one, we're going to give some sample data through instances of a data set, okay? And we're going to ask our H2 learner and our H10 learner to learn a polynomial. Okay, so this is the crux of this section as well, all right? It's to think about the overfit measure, which is a measure of how bad it was to use H10 over H2, okay? And it has the same look and feel as this set of diagrams that we saw earlier, okay? The key difference is that now we are being able to differentiate different types of information, okay? We can think about stochastic noise, which is, let's say the data points are measured incorrectly, you know, they're off in their X and Y values. So that means, for example, here, the points, let's go back here, okay? The points are not measured exactly on the X and Y where they are supposed to be, okay? As well as deterministic noise, okay? Deterministic noise has to deal with what we are saying is as bias, okay? This is bias, okay? How much worse is it to use a certain representation class over another one? Okay, so when we can say, as we go from left to right on both graphs, okay, from this side to this side, this side to this side, generally we can see it is better to use H10, okay, because this measure is 0 when it's yellow. When it's positive, it means H10 was worse, so that's red color. And when it's blue, it means it was better actually to use H10, okay? So it has the same general trend as what we saw before over here, which said that when we get closer to this side, where we have more data points, it starts to become worthwhile on this white part for us to use H10, okay? And you can see that as the color changes from this dark red to this light blue or dark blue over here. Okay, now when we have a function, okay, and we say this function is going to be our y value plus some sigma squared, some Gaussian noise, right? We can also vary this under control conditions, okay? So if we add more noise, we sprinkle more Gaussian noise and the points scatter a little bit more from some type of Brownian motion type of thing, then we can say our overfitting also will tend to go up, right? Because our measurements aren't exact. Every data set that we get, even if it's the same data points, because of stochastic noise, we are measuring them incorrectly, okay? So our hyperplanes that we're going to come out with are more noisy, okay? So that is going to, again, increase as our noise level goes up. And so you can see we're going from a better use of H10 to a worse use to bad, right? Even if we have a lot of data points and we have a lot of noise, then it's better to use a weaker function, okay? So again here, like we said at the beginning of the lecture, it's not just the quantity of points, okay? It's not just the M, okay? It is also the quality of those points, right? So if we get a lot of noise, then we're in trouble, okay? The other thing is deterministic noise, okay? What is deterministic noise? That means the target function that we're building, okay? The target function that we have. Let's say we have here a 10th order polynomial, a 50th order polynomial, or a 100th order polynomial, okay? As we increase the complexity of the polynomial, we get more and more overfitting, okay? So that is a problem because when we sample points from this target function, you know, we will still not be able to fit the function very well, okay? Because the sample of points that we get from, let's say, this 100th order polynomial, and we set a 10th order polynomial to approximate it, it will still go wild at the tails, right? It'll be able to fit some points, but you'll see something like this as a result, okay? Whereas our H2 simply, it can't fit anything very well, so it's going to do something right in the middle, okay? Nothing very good, okay? But at least it doesn't have these wild variations here, okay? So that's why in the deterministic noise case, we will have this fluctuation, okay? All right. So I want to get through a little bit of this part where we talk about the analysis. Then I'll turn to your questions. Okay. I'm sorry we're a little late here. Okay. So again, we have several different parts of noise, and we need to be clear about this. Okay. We have data noise. Okay, meaning that we have errors in measuring the data. Nothing we can do about that. Okay. So we have a model, but the points are fuzzed out. Okay. There are fluctuations that no matter what we do, we can't do anything about. Okay, so even if we sample the same data points, our measurement error is off. So we might get different Ds, even though we're looking at the same point. Okay, so you can think about that. You know, you're standing in the same place in GPS, and then every 5 seconds, it's telling you you're in a different location. Okay. There's also deterministic noise. Okay, so deterministic noise is where we are talking about bias. Okay. So this is where we're using a very simplified model like H0 to approximate a complex model, okay? So we can't do it, right? Our target function is too complex. We have chosen either advertently or inadvertently a model that underfits, that cannot fit the entire function, okay? And so whatever we cannot fit, okay, as to the best approximation, again, here's our H bar, our best average function that we have from all of the data samples, okay, is going to be regarded as noise, right? Because we just can't model it. Sorry, if I use, you know, 100 triangles to approximate this, good luck. This is the best I can do, okay? So it's a part of F that we lack the capacity to model. Okay, so both types of these things are problems. We have deterministic noise, which is our bias, and our stochastic noise, which is not our variance. Okay, here it's really stochastic noise. Okay, it's our sigma squared. Okay, and you're wondering, okay, I learned bias and variance. Where's the variance? Okay, so when we do the decomposition, we will be able to look at that. Okay, so it turns out that when we do our decomposition, we end up with the same thing. We will end up with source that is completely stochastic noise, all right? Our deterministic noise, which is to say that our model might be underpowered. Our average function drawn over all possible data sets still does not quite come and capture the right semantics of the target function, okay? And then we have our variance, right? The variance is the only term that's dependent on the data set, right? This doesn't depend on the data set. That's just error, regardless of what's going on, okay? This doesn't depend on the data set because we're averaging over all data sets, the general hypothesis, okay? So this part, the variance, has to deal with the particular data set that you were lucky enough to observe to train your model, okay? Unfortunately, it is a sample. It's not the whole data that you have access to the actual target function. So when you are restricted to the sample, how bad or how much variation do you get, right? The variation comes from the square term between the actual hypothesis, right, drawn from the data set, the optimal one, and the one that we would get if we were to draw unlimited amounts of data from our target function, okay? So there's actually 3 different things that we need to think about, okay? So we can go through the KNN regression with noise. It's not particularly complicated. The only thing here is that we did say that we are going to assume that all the points, the neighboring points, are fixed neighbors, okay? So if you have questions about this, I can go over it with you. But yeah, I think given the amount of time that we have, we're supposed to already end lecture. Let me turn to your questions, okay? And then we can go towards that. Okay, let me do one slide, sorry, to say what you're looking at this week, okay? So when we have noise, right, of any sort, okay, whether it's stochastic noise or deterministic noise, we will often get overfitting, okay? Why is that? Because a learner only sees data. It doesn't have any way of deciding whether that data is partially signal or partially noise, okay? It's just data, so it's going to try to fit everything, okay? So when you have a very powerful model with lots of knobs, you can adjust those knobs to make sure you get every target point as best as possible. And that often causes overfitting because of these two properties, because of deterministic noise and because of stochastic noise, okay? And this week in lecture, which you're studying now, is to figure out two ways of doing this, okay? By restraining the model, okay? That means instead of choosing all possible hypotheses, there are only a certain set of hypotheses that are good, okay, that we think are plausible Fs. So we're going to ignore others, okay? And then here, when we have validation, it's basically finding several different ways of approximating how bad our fit is by taking the data set and splitting it in multiple ways to check whether we are getting good generalization or not. Okay, let's go back to one slide because I think Li Shuo and Zheng Lo, Hong Zhen said something about that part. So let's go back to that chart. Okay, this one here. Okay. Okay, so when we increase the number of data points, okay, that's going from left to right, right? Our overfitting goes down, right? Because we're going from red to blue. The blue is better for H10, okay? So that's generally what's happening, okay? So that's why deep learning models work well, because they can harness a lot of data, okay? And because deep models are generally have lots and lots of parameters, it's not uncommon for us to study deep learning models with millions or billions of parameters, okay? But you can see in this lecture today, we talked about models with 1 or 2 parameters, right? Just 1 or 2, and we can demonstrate this idea of overfitting. Okay, so both of you are right? So data points, when number of data points increases, overfitting decreases, right? The overfitting gets less. So it's good to have more data, right? And that's the same as what Li Shuo said, right? So if I have increased data, I lessen the amount of overfitting, okay? So that's generally correct. So what we have to worry about here is also these 2 points, right? When the stochastic noise, when the noise level goes up, my data quality is worse, overfitting will recur more, right? Because there's more measured error. I don't know how much is due to my signal and how much is due to my noise, right? So when the noise component gets worse, overfitting will, of course, because it doesn't know any better, it'll fit the whole thing. And much of that signal, that data is actually not signal, it's noise. So overfitting will occur worse. When we have deterministic noise, when we have a low powered classifier, then we will also have overfitting, right? Because we don't have enough complexity in our model to accomplish that, okay? All right. I'll come back to these slides if you have more questions, but let's turn to our Ask Me Anything. I have to go back and pull up the browser. Sorry about that. Go Chrome. Okay, and then go. So if you need to go, don't worry. You can go, and then if you want to watch the rest of the lecture later, it is recorded. But if you want to stay on and then go through some of the questions, we can try to do that. Okay? Okay, so let's see, we're already on here. So we're going to look at this one, right? So I think we already covered this. Y is Y times theta x plus b, the distance between the hyperplane and the point. This is the inequality that we consider, okay? To just say that we want the hyperplane to classify with a value above 1, okay, for all points that are positive, and a value below -1 for anything under the hyperplane. Okay, so we're going to hide that one. Okay, tutorial 3, question 4. Okay, I'll take this one in a minute. Okay, I want to finish some more of the lecture one so we don't have to switch around so much. Okay, can you explain why deterministic noise increases, overfitting increases again? Okay, so yes, let's go do that. So we just looked at that one. Okay, so that's here. So here we're looking at the deterministic noise part, right? So let's see whether we can blow this up, right? So here we're looking at on the y-axis, all right, is the target complexity of the class that we're trying to do. So we have a linear model, and we're saying it has how many coefficients? Like 0, 2, 10, or 50. So this is a 50th order polynomial. This part over here is 10, okay? So that's that part. So I'll explain this in a minute. So we said that when we have deterministic noise, okay, meaning that we choose an underpowered learner to try to learn a complex target function, we get more overfitting, okay? And you can see this here, right? As we're going vertically, okay, on this graph, okay? You can see the colors get from dark blue to light blue and then eventually red, okay? And that is because the target complexity is creating points that are harder and harder for the learner to fit, okay? So when we have a high degree of target complexity, using a more complex target function can result in more overfitting, okay? So this red part over here is basically saying, even though, you know, I'm using H10 and H2 to approximate, let's say, a 50th order polynomial, which is this part, or a 100th order polynomial here, okay? It was still better in this oval region to choose H2. H2 was better, okay? And that is because of what we talked about before, right? When we use the sine wave, right? Our sine wave here, and we saw if we only got 2 points, we don't have enough points. When we draw our sample, it's going to lead to an output of high variance, okay? So this high variance is why our overfitting happens, right? We are not able to fit much at all with H2, but our H10 can fit better, but it gets high variance, right? So that leads us to having this overfitting going up, okay? So very curiously, if you look at this graph, you should be able to decode more of it, all right? So you can think about, for example, you look at this graph, there are actually two very interesting parts, right? There's this part which is due to a polynomial of size 10, and there's this other part that is due to a polynomial of size 2. And that's not coincidental at all. That makes a lot of sense because the two classes of functions that we were comparing in the top of this graph was h-test of h10 minus h-test of h2, right? So when we come down to this part, it does make a lot of sense, right? So let's look at this bottom part here, okay? So this says when we have an H2, okay, H2 target function, and I use either H10 or H2 to approximate it, when I have enough points, both of these work just fine, right? No problem at all, okay? No problem at all, because they both can capture H2s, right? H10 will just set all of the coefficients from theta 10 to theta 2 to 0, right? And then theta 1 and theta 0 will have some number that's identical to our H2, okay? So that explains why there's green all the way over here, okay? All right, so that's clear. But what about this funny looking part over here, okay? This is H10, right? So H10 looks like this, right? It sort of like goes up like this. So in this part, H2 is better. In this part, H10 is better. So why is that? Okay, when I have too few data points, okay, which is on this, you know, this side of the graph, okay, even though I have H10, okay, I cannot fit something very well, okay? I don't have enough points, okay? So when I have exactly H10 to H2, somewhere in this margin here, okay, this area here, okay? This is the class of target complexity, right? Which is between H10 and H2. And you can see very rapidly over here, I can no longer use a second order polynomial to capture H3 through H10 very well. It underfits, okay? I don't have enough knobs to capture any regularity. The H10 here is doing pretty well, okay? So that's why you can see that there is this nice line across here, which is to say H10, as long as you give me, you know, enough data points, I can capture H10 very well, okay? So all the way up to around here or so. And then up to this point, it's basically still saying that if you give me a target complexity that's bigger than 10, okay, 12, 15, or whatever, now both of these models can no longer fit perfectly, right? H10 and H2 both cannot fit H50, H15, or anything, okay? But because of the variability in H10, H10 has a lot more sensitivity to the exact data set, okay? Because H2, well, basically can't express a lot, okay? That variability is what's causing all of this red part here, okay? This is basically due to H10's a huge variance error, okay? Okay, H2 doesn't have so much variance error just because it's not a very powerful classifier, okay? So that's how you understand this graph, okay? So you should be able to understand why these things look the way they do, okay? So if you have more questions about this graph, please put it on chat so I can see it. Yes, higher variance usually means more overfitting. Yes, higher variance usually means more overfitting. Yeah, variance is a much bigger problem for complex classifiers because, again, they have more knobs that can be set, right? The more parameters that you have, the more ways you can fit the signal, okay? You can think about it this way. Let me just try to give you an intuitive understanding, okay? So, you know, let's just, okay, that wasn't so good. Let me pull this out. Okay, blank. All right. So we can think about a signal. Okay, let's say I have some signal. Okay, and this signal can be partially due to actual measurement and partially due to noise. Okay, so my sigma squared. Okay, so when I increase the amount of noise, okay, from here to something like this, okay, more noise and less signal, okay, the fit of the model is still going to proceed the same way because our classifier doesn't have any idea which part is the signal and which part is the noise, okay? So in a more powerful model, okay, when we have more noise, it'll be reflected even more strongly in the fitting of the model, okay? So that means as you increase our complexity class, as script H increases in complexity, the part that's more responsible for fitting the noise will be compounded, right? So it'll get worse and worse, okay? And that's why the variance will become even more large, okay? Not just for the noise, but because of the sampling of the data set, okay? So we can take this away too and think about the case of the bias and the variance, okay? As the variance enlarges because of the reliance on the sample for giving you the right values, you'll get more error that way, okay? All right, very good. So let's go back, okay? What is happening in the slides, graph 40 and 41? What does the dotted line represent? Let's go back there. 40 and 41. Okay, so this is basically just looking at the case of these types of error curves that we saw earlier. This is the same learning curve as the one that you saw. Oh no, it froze again. Okay, no, it's still back. Okay, good. I thought my computer died for a second. As the same as this type of curve, okay? So let's take a look at this. Okay, so again, we're looking at the training, the loss of our model, right? So when we have a simple model, okay, it won't be able to fit very well. So in the limit, as we get infinite number of samples, our model won't be able to fit the target function very well, okay? So that's why there's a discrepancy between here and here. Okay, this is the complex model is able to get lower loss because again, it can fit the signal, the entire data better. okay? But because we have enough samples, the noise will go away, right? Because when we think about stochastic noise, or sigma squared, right? We usually think of noise as normally distributed. So in the face of large data, the noise terms will cancel out, right? Because they'll average out to 0, okay? So we can only look at how good the fit of the model is, right? So when you have a complex model, we'll be able to fit our data better. And so that means our ultimate loss, okay, will be lower in this case. This is why we have a difference between this loss value and this loss value, okay? Because we have a more simple or more complex model, okay? The other part that we were showing you on the other slides is that J-test, our test error, falls a lot faster at the beginning with a simple model, okay? And that's because the variance is not so big, okay? So because the variance is large on this type of complex model, we have all of these points over here. If we overlaid this point, this graph on the left side with the one on the right, you would see it looks a little bit like this, right? So that this point here, sorry, not like that, maybe a little bit more like that, okay? So that the variance problem is less acute here, okay? So everything above this dotted line is the variance, okay? Variance, error. And everything below the line is bias error, okay? This is a simplified model, right? Bias error is easy to understand, right? It's saying that how powerful is my model? If my model is powerful enough to approximate the function well, okay, I will have lower error, right? Because I can approximate it well, okay? In the limit, okay, in the limit, it will reach some plateau. That plateau is either 0 if the target function is actually inside the hypothesis class, or at some positive value because the hypothesis class that I picked isn't strong enough, okay, to counter that. So both of these models, in this case, a complex model and a simple model, don't actually contain the target function. That's why I have a non-zero training error at the end, right? Training error just basically means I cannot get all of the examples right, okay, even in the face of infinite data, okay, because I can't fit it, okay? And the other source of error, as we said, this comes above the line, is dependence on the actual data sampled, right? So I get a particular data sample, I learn a model from it, but because that sample is not representative of the entire data, I have some variance error, okay? That variance error causes the J-test not to generalize well, right? Because the test data comes from the same distribution, but it's another data set, right? So if I have two different data sets and they give me different hypotheses, right? Then of course I will have variance error, okay? So that's how we understand these two graphs, okay? So that it's the same simple, similar type of graph as we saw on the beginning in the other graph above here, okay? When we were looking at these two graphs over here. Okay, so we're finished that. Okay, okay. So yeah, this one is done. Okay, so okay. Deterministic noise increases, overfitting increases. Okay. Yeah, I think I answered this already. So we went over those slides a little bit. So let's go back. Okay. All right. Hi, Prof. If 15 points given are noiseless, does that mean H10 can definitely win? Yes, that is the case, right? If you have a target function which are noiseless, okay, and that H10 and the target function is actually of H10, right? Then all of the points that it gets can exactly replicate the coefficients of that function. So it will mean H10 can definitely fit, right? So that is the case when it's noiseless and when the target function is exactly in the hypothesis set and you have sufficient number of points to determine all of the coefficients, okay? If I gave you 5 points or 8 points, okay, maybe I still wouldn't be able to fit the H10 properly, right? Because it's underdetermined. There are many different possible ways I can set H10 if I give you only 8 points, for example, okay? So I'll finish that one. Okay, so I also talked about Z-space and SVM, so I'll get rid of this. Okay, so SVM selects support vectors by doing what we just talked about earlier, which is on that part. Okay, so looking at a data set, okay, and trying to determine which points are closest to a hyperplane, right? So we're going to determine where the points are, which ones are closest to each other that are of different classes, right? So I'm going to say that this class and this class are different, right? So I want to make sure that I have a hyperplane that is trying to bisect the divider between these, okay? So again, what we do in the SVM, okay, let's see, yep. Here is just to determine that all of the points that are in one class have a positive value, all of the points on the bottom class have to be a negative value, and we try to optimize this. We try to optimize it so that we get a case where we can have all of these points be this way, and also to guarantee that the points closest to the hyperplane have a unit value distance. Otherwise, we can vacuously scale this. We can just say, with these types of, with these two inequalities, I can set arbitrary distances. I could set this equal to 2, I could set it equal to 20, and I would just get different solutions that actually mean the same thing. So we just constrain it to unit value just to make it simple. Okay, the actual way that the SVM does the support vector calculation is related to a quadratic programming. It's basically solving a set of equations to find out which points are on the support vector by determining a set of coefficients, where those coefficients tell you whether it is actually on the support, meaning on the hyperplane boundaries or not. Okay, so we'll close that. Okay. Okay, optimistic and pessimistic bias. I think we will get to this next week's lecture, right? Is in week 6. So we will do that in the next help lesson, right? So when we talk about this part, we will understand why validation gives you an optimistic bias, because you're using the validation results to actually choose the model. That's why it does that, okay? Yes, there are model code for the Collab notebook. So if you go to the emails or to the material section, there is, you know, the evaluated output. So I'll just show you that since we're here. Right, so if you go to the Collab notebooks and solution, these are slowly getting released to you. So at the bottom, you can see the archival versions of 1, 2, and 3. They have, as far as I understand, because I asked the TAs to do that, put in the answers for the computations. So if you're not sure about why you got something wrong, if your TAs weren't able to give you a helpful comment, then you can also raise it up there. You can say, I still don't understand what you mean by that. You can just make a comment on your assessment. They should get back to you. But you might also refer to the answer keys, okay? And the answer keys, just let me make it clear to you, those answer keys are provided for you. Please don't put them on GitHub. Please don't put them in a public repo, because we need these set of notebooks to help teach other students. Even if you believe that students won't cheat, as soon as you search for an item and Google can pull up the answer, then, basically everyone doesn't have a good time because it's just too easy to get the right answer without trying. So the whole point on collab notebooks is, again, we're not trying to incentivize you to cheat. It's not worth very much. It's just for you to do and for you to understand and to practice, okay? We're not really assessing you with that. It's just formative grades to make sure you participate, okay? So please, please do the right thing. Do the notebooks for practice. Don't worry if you don't get everything right. They're not there to penalize you. They're for you to practice and get better. Okay. All right. So we're done with that one. Hide. And then we'll go to the tutorial ones, okay? Because there are some parts about this. Okay. One more from the pre-lecture, sorry. Pre-lecture slide 26. Okay. So this was about the margin violation, right? So we're basically saying here that there is something wrong, right? When we take the class of the point, and we take the hyperplane, and we multiply them together, and we get a violation because it's not above 1. Remember, we did this type of multiplication to collapse our positive and our negative classes into a single case, right? So it needs to be greater than 0 in the case of the perceptron. In the case of the support vector machine, again, we want it to fall outside of the margin, so we define it to be greater or equal to 1, right? If the distance is exactly 1, that means it's a support vector. It lands right on the side of the highway. If it's greater than 1, that means it's somewhere distant and we don't care about it, okay? So when this thing fails, then we are saying that we're going to have a penalty, okay? We are basically saying, okay, when we allow some failure, okay, but we're going to put it into a term. So we're going to solve this inequality when we actually create the SVM, okay? We're going to say, I want everything to be at least at a distance of 1, but if you are not able to make a distance of 1, never mind. I will subtract that distance that you violated from the inequality, and I will still let you satisfy it, okay? So this is the points where there is a penalty, right? So where xi is greater than or equal to 0, any of these points that are sitting in the hyperplane, that means there is a problem, right? It's in the wrong place. So these soft errors are on particular points, and we just total them up, okay, to get a penalty function. And that penalty figures right here, right? So we total up all of the penalties, and then we have a multiplier to say how much I dislike or I don't mind, tolerance of how much a violation that I have. And then I have the original boundary, okay? This is the multiplication that allows us to decide where the boundary lies, okay, between the positive and negative points. It's just the multiplication of the weights of the hyperplane as it exists, and to try to minimize this function overall. Okay. Okay, so we'll hide that. Let us go to the tutorial. Okay, so let's see whether we can do that in the remaining minutes. Okay, again, if I cannot explain very well, never mind, we will do it through questions on the forum because I have everything there, okay? So let's see. Oh, I have the solutions here, right? So let's go. Okay, so which question did you guys ask about? Let's go see. Tutorial free question 4. Okay, nonlinear transforms. Okay, so here we've got a nonlinear transform, right? Basically we're considering taking a bias term that's just going to sit there, doesn't do anything, as well as 2D coordinates x and x2, x1 and x2, and then map them to something like this. So I'm going to take the square of x1 and the square of x2 and do something like that, right? And then what I want to do is draw and show the boundaries of what it looks like in X, right? So again, in the Z space, right? In the Z space, we have something that's a linear classifier, right? So I have x1 here squared and x2 here squared. Okay, these are the two coordinate systems, and I have another coordinate which is a bias term. So this is a 3D space. I'm only going to draw it in 2D, and I have a hyperplane, right? That's going to separate things less than 1 and greater than 0 and less than 0. So maybe the hyperplane is facing this way. So all values over here are positive. All values here are negative. Okay. So what we want to do is figure out what the boundary looks like in X, right? So I'm going to take this hyperplane and map it back to X space, right? So hopefully you remember the equation of a parabola. And if you don't, it's not a big deal, okay? You can look it up. And then you'll see that you get something like x squared, okay? X squared minus y squared equals 0, or something like that, okay? So when we have this, we can draw a parabola, okay? And then depending on which way it's set, whether it's y squared, x squared equals 0, you get either a north-south parabola or a east-west parabola, okay? And again, depending on whether you set your inequality to be greater than or equal to, then the hyperplane is either facing this way or this way, meaning that the positive points, let me erase, the positive points are over here in the case of the hyperplane facing like that, or whether the hyperplane is facing the opposite direction, right, over here, and we have positive points here and positive points here, okay? So this is a hyperbola, right? Okay, that's in some of the cases when I have this case here, right, where the thetas for these two values in X space are larger than, the thetas for Z space are greater or equal to plus and minus, right? Okay, so that's the case where I have a parabola where there's 1 plus and 1 minus, right? When it is both positive, okay, that's also very simple, right? Because we know what that would mean. That means I have something like x squared plus y squared equals 0, right? And depending on what this bias term is, what our coefficient for the bias term, right? So this is our x1, our theta 1, our theta 2, and our theta 0, which is times 1, right? Because that's our bias term. Then we would get different types of ellipsoids, right? So here we have the x value being bigger, right? And the y value being smaller. And so we would get an ellipse like this, but it depends on what these coefficients are for, as long as they're both positive, right? So I have a something x squared positive, something y squared positive equals something positive, and I would get that. Okay. So that is the answer to this set, right? If you have other values, you might get a case where you get something like this, where you have everything that are just single lines, and you're either looking at classification boundaries that are going out. Okay, if the positive norm of the hyperplane is facing that way, or it could be on the other side. Okay, also possible that it's facing in. Okay, facing in, which is this way, right? And then you would have all the positive values in the middle. Okay? All right, so I hope that solved your problem for that. Okay. All right, let me see, I want to go back. Okay, that was question 4. Okay, we went over this already. And we'll go back to question 1 of tutorial 3. Okay, tutorial 3 is on the same slide. Okay, so let's go back here. Okay, so this is talking about logistic regression, right? So here, which of the following evaluation metrics cannot be applied in the case of logistic regression? Okay, so why aren't you able to use mean squared error? Okay, because mean squared error is what we use for regression, right? But it's not for classification. We already know logistic regression is actually for classification. It's to give us some idea of the probability, right? Probability of a class. And here, the important part is when we think about probability, we don't want squared error, okay? Something is either wrong or it's right. We're not going to say how much wrong is it or how little wrong is it. It's just wrong, okay? So we need to make sure we do this properly. If you're not clear about this, actually, if you have 20 minutes, I suggest you take a look at Eugene's optional material. So this last week, Eugene, in the optional tutorials, not optional, optional videos for lecture 5, opt 01, oh no, this week, sorry, lecture 6, opt 1 and opt 2. These explain this logistic regression problem in a lot nicer way than I have to do here, okay? So all of these other ones you can use. You may not know what some of these are, okay, like AUC, ROC, but that is another set of metrics you can use. It basically measures how this is called area under the curve. And this is a radar receiving operator characteristics, but no one really cares what that part of it means, okay? So area under the curve just looks at a plot of sensitivity versus selectivity and looks at the area under the curve. So a larger area is a better AUC. And so I'm not going to go into it much, but basically, if you have good AUC, it corresponds to good accuracy. So this is also another metric that you can use. Okay. All right, then I think that is about it. It's sorry, it's quite late. I apologize, but I think this is a really important lecture. It's one of the most fundamental parts of machine learning is to understand the bias variance trade-off. So once you have that, then you're all good, okay? Because much of what we want you to do in the analysis, much as what you hear in guest lectures, are a lot about bias variance and overfitting. These three topics are really, really the key things we want you to walk away from the theory part of our machine learning course, okay? And with that, I think we're done. So thanks for staying with me until 6:19. I hope you're doing well and getting ready on your other work for classes, okay? Great. So I'll see you guys next time. We will have another help session during recess week to cover W06 before the test is here, okay? Cheers, everyone. Take care. Stay safe.